Diabetes mellitus is a major health problem among the working-age population, affecting about 537 million people worldwide. Diabetic retinopathy is one of the major complications of diabetes mellitus, and diabetic macular edema is the first cause of visual impairment in patients. Optical coherence tomography has become the gold standard in the management of diabetic macular edema. It repeatedly provides quantitative and qualitative information on the morphological characteristics of the retina. OCT has significantly increased our ability to diagnose even mild edema, thus increasing the number of images to analyze. This analysis is time-consuming and often characterized by interoperator variability. Artificial intelligence greatly simplifies and speeds up the evaluation of large amounts of data, such as the new biomarkers provided by OCT. A deep learning software has been developed to simultaneously analyze and quantify the major OCT biomarkers in diabetic macular edema. The software allows the segmentation of all retinal layers and quantifies both the intra and subretinal fluid, both on linear and volumetric scans, and also allows the topographic localization of the intraretinal fluid in different macular ETDRS rings. Furthermore, it can quantify the hyperreflective foci throughout the retinal thickness, which are signs of neuroretinal inflammation, and quantify the interruption of the external limiting membrane and the ellipsoid zone in the central scan passing through the fovea. The algorithm showed optimal performance on a sample of more than 300 eyes affected by diabetic macular edema from 4 different centers in the detection of the different biomarkers, with an almost perfect agreement between the software and the clinical evaluation. The automatic quantification of all parameters compared to an expert operator was coincident in approximately 95% of cases, without significant differences among centers. The same was found for the automatic centering of the fovea and the segmentation of retinal layers. The presence of macular fluid represents the most important diagnostic retreatment criterion in the management of patients with exudative macular disease, and the evaluation of the fluid status on OCT has become a routine daily task for ophthalmologists. The external limiting membrane and the ellipsoid zone have an independent primary role in the evaluation of diabetic macular edema, particularly from a visual prognosis point of view. Finally, hyperreflective retinal foci are an established sign of retinal neuroinflammation. They contribute to the characterization of different phenotypes of edema and require different treatments. We can also relate the changes in the different biomarkers at different time points and visualize intuitive graphs of the progression of the edema over time, providing an overall picture of the patient even over long time periods. This may help us to look at the course of the disease in a comprehensive way, to understand, for example, a reduced response to treatment based not only on fluids, but on other markers such as hyperreflective foci. In the future, implementation with new biomarkers and device tools will further expand the application of AI. In any case, we now have a new instrument to improve our clinical practice towards a more targeted management of diabetic macular edema.